Hello once again, class, and welcome to another mock lecture. Today we're going to be discussing what the basic counting rule is. And to do that, I'm going to remind us about a tree diagram that we drew in the last video that I uploaded, which was about the number of possible outcomes for a bag of marbles containing 2 red, 1 blue, and 1 yellow, wherein you're drawing 3 of them. And based on the tree diagram, we figured out that there's 24 possible outcomes. Now, a tree diagram is a great way to visualize outcomes and sample spaces, right? It's a very structured approach to coming up with that, and you can actually see, based on maybe I draw the blue marble first, well then what can I draw second and third? So it's a nice breakdown for each individualized case that could potentially happen. But also, a tree diagram is evidence for what the basic counting rule or basic counting principle actually says, which is that if we need to pick 2 things, and there are m choices for the first thing and n choices for the second, then the total number of choices that you have is the multiplication between m and n. Okay, now you might say, well, wait, hold on a second. In this example, there's actually 3 choices, right? You're drawing 3 different marbles. And okay, you can expand the basic counting rule to however many things that you're picking. So I said, as kind of a follow-up, if there's a third thing that you need to pick, and there are p choices, right, for that third thing, then the total number of choices would be m times n times p. Essentially, however many things that you're picking, if you know how many choices you have at each thing that you're picking, you just find the product of all of those things, the number of all those things, and that would be the total number of choices that you have. So in our example, where we had 4 marbles, the first choice, right, we have 4 things to choose from, and let's say we choose one of the red ones. Again, without loss of generality, like it doesn't matter what we choose, we're just pretending. I'm just crossing one off to show you one is gone. The second choice has 3 possible marbles that we could choose from, so there's 3 ways to choose that second marble. And let's say that that one was the yellow one. Then the last choice, there's only 2 marbles left, so there's only 2 ways to make that third choice, and so the total number of ways, and let's say we chose the other red one, the total number of ways that we could choose these 3 marbles from 4 of them would be 4 times 3 times 2, which is 12 times 2, which is 24, which is how many that there were, right? That's the total number of outcomes that we had when we were drawing 3 marbles from starting with a bag of 4 of them. Okay, so that's how the basic counting principle works. Let's look at some quick examples.
We went 500 miles.
Hey, was I supposed to bring the ticket to the sandwiches?
All right, example number 1. Suppose for your next term you need to take 4 classes. You have to take a math class, a science class, an English class, and then you also have to take an elective. And let's say that there's 3 different math classes you could choose from, 5 different science classes you could choose from, 4 different English classes that you could choose from, and then there's 8 different electives that you could choose from. The question is, how many different schedules can you make? And so for me, when I'm doing this and I'm trying to figure out, well, how many possible outcomes are there? I like to set up kind of a space diagram. I don't even know. What would you call this? I like to have placeholders for the multiplication that's about to happen here. And all I'm going to do in each of these spaces is I'm going to multiply however many choices I have for each of the different classes that I could take. So if we fill in all of those choices, right, there's 3 math classes that you could take, there's 5 science, 4 English, and 8 electives. You just multiply all those things together and you get that there's 480 different schedules that you could make. Although I guess we're kind of also supposing that there's no time conflict between any of these, so let's kind of ignore that part of the whole situation. But in any case, there'd be 480 different schedules that you could make, assuming none of them conflicted with each other. Okay, that's it. Example number 2. What's the probability of drawing an ace and then a king in a standard deck of cards? Now this is a good problem to talk about because we have to count 2 different things. It's a probability, first and foremost, so we have to figure out what are the number of ways that you can even draw 2 cards in a standard deck of cards, and that's your denominator. But then your numerator would be, well, how many ways are there to draw an ace and then a king? So we'll answer the denominator part first. The number of ways there are to draw 2 cards from a deck of 52, your first card, you have 52 cards to choose from, or that you could be dealt, because it's random, right? And then once you're dealt a card, there's now only 51 possibilities for that second card. So your denominator would just be 52 times 51. Now, the numerator is actually a little bit different because you're drawing two different cards. If we were drawing an ace and then another ace, we'd be drawing two cards. We'd say, well, there's 4 aces at first, but then you're given one of the aces, so then there's only 3 aces left. But we're not drawing an ace and then another ace. We're drawing an ace and then a king. The number of kings left in the deck, if the first card you're given is an ace, is still 4, right? It's unaffected by that. So you would just have to multiply 4 by 4. And that would be our numerator, right? 4 times 4. That's it, right? 4 times 4 is 16. 52 times 51 is 2,652, which I went ahead and figured out is 0.00603332, which is not a strong probability of being dealt an ace and then a king, but there you go. You got about a 0.6% chance of being dealt an ace and then a king if you were to randomly deal yourself 2 cards. All right, for the last example, we're going to look at suppose you're choosing an outfit for the day and you have 2 pairs of pants, 3 shirts, and 2 pairs of shoes. How many different outfits could you wear? Well, just using the basic counting rule, you have some option for number of pants, some options for number of shirts, and some amount of options for shoes. You just multiply all those things together and you get 12 different outfits. This is what the tree diagram would look like, and there are indeed 12 things right that are listed here. So that's it. Just kind of a short video talking about the basic counting rule and how you can visualize it with tree diagrams. If you guys have any questions, please leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.